Sorts. Sorts are used to put data in order. Selection sort starts at index 0 and works its way to the end of the list. At each index, the sort will find the location of the smallest value from x, the current index, to the end of the list, and then swap the values at x, the current location, and where the smallest value is. The effect of this swap is putting the correct value into location x. Some notes: selection sort is slow. In fact, it's the slowest of the sorts we're going to cover. In this example, we're going to walk through how it would work. So let me get the pen out. We're trying to fix location 0. So what our sort would do is find the location of the smallest value over here, which would be at 4. It would swap 0 and 4. 3 would go here, and now 4 would be placed at the end. It's not putting 4 in the correct spot, it's putting 3 in the correct spot. 3 is going to be unchanged. We are now looking at location 1. 1 needs to be corrected. We're going to find the smallest value in this range and swap that value into location 1. 1 and 3 have to be swapped because 4 is the smallest value in this list. So 4 goes here and 7 goes here. Then we have 6 and then 9. On the next pass, we're fixing location 2. The smallest value is 6. It swaps with itself. So after the third pass, nothing has changed because location 2 swaps with location 2. On the next pass, we're trying to fix location 3. So all of these are the same because they've already been fixed. And in location 3, we find that the 7 has the smallest value. So we swap 9 and 7. We swap locations 3 and 4. And it just happened that we always swapped with the end location. That is not always going to be the case. It's just in this example it turned out that way. And now we do not have to fix location 4, because if locations 0 through 3 all have the correct values in order, 4 has to be in order. The pseudocode. We work from 0 to the end, or the end minus 1. You do not actually have to process the end because it won't find anybody after it that's smaller than itself. We have to keep track of the location where the minimum is. We currently believe in the list the first value we look at will be the minimum, so location A is the minimum. Then we do a for loop that goes from A plus 1, everything after our current location, all the way to the end. If location B has a smaller value than where we currently believe the minimum's at, then the min location should become B because it is a new small item that we found. When this inner for loop finishes, minimum index will be correct. So we swap the values at min index and A, the location we're trying to fix, putting the smallest value into location A. After that, we move on to the next value of A, so we move one index deeper. Insertion sort. Insertion sort starts at index 1. The last one started at index 0, so this one starts at index 1. And it works its way to the end of the list, just like the last one did. At each index, it will move the value to the right. At each index, it will move the value to the left if needed, so that the values in locations 0 to x, the current location, are in order. After processing the last index, all the values will be in order. Notes: insertion sorts are faster than selection sorts, but are still fairly slow. Something else you should know: insertion sort is the only sort that works really fast on data sets that are already in order or almost already in order. So if you're looking at a list that's already in order, all the other ones are still going to brute force and try to sort it and not realize it's sorted. Insertion sort is the only one that figures out, hey, it's sorted, I don't need to do anything, and doesn't waste a whole lot of time. So on this one, we're going to start at index 1, not 0. And we're going to say, let's put 1 in the correct spot to the left. Well, looking at only these values, is 7 in the correct spot? Yes. So we write 4 and 7. These are left alone. That's an ugly 9. Alright, now we're going to fix location 2. Looking at 4, 7, 6, is 6 in the right spot? No, we're going to take it and insert it before the 7. So our new list is going to be 4, 6, 7, 9, 3. On our next pass, we're fixing location 3, which is the 9, and it looks like it's already in order, so we just write it down again. 4, 6, 7, 9, 3. On our final pass, we're going to fix location 4. And we look at this 3 and we're like, whoa, that's in the wrong spot. So we're going to insert it right before the 4, sliding everything else over. So it would be 3, 4, 6, 7, 9. The pseudocode for this. The pseudocode for this is pretty complicated. So we start at position I, which is 1, and we go all the way to the end. Temp, the value that we're trying to place, equals the data at I. J equals the index that we're currently on. While the index is bigger than or equal to 0, we move forward. While J is bigger than or equal to 0, and the guy before J is bigger than the value that we're trying to place, data J becomes the value before it, and J moves backwards. This is how we're copying values over. So in our list, if we had 4, 6, 7, 3, what's actually happening is the 7 gets copied in and placed here. So then we still have a 7. Then the 6 gets copied and placed where the 7's at. So you have 2 6s. Then the 4 gets copied over here. Notice every value shifted 1 to the right. And now the 3 has to be placed. The 3 will take the final position. So data J equals temp. So after moving values over, data at position J, the place where the value should be, equals the value that was originally in position I. This is fairly complicated, and after a few examples, you'll kind of see how this works. This is one we'll work in class and follow the I's and J's as well. Merge sort. Merge sort works by cutting the list in half, and then cutting those lists in half, so on until there are n lists, which n would be the size of our data set, of size 1. The lists are then merged back together and put into correct order, starting with the ones that were most recently split. At the last stage of the algorithm, you have to put 2 ordered lists together, each containing half of the original list's data. Okay. Now real quick, I know that was a mouthful. Before I move on, you don't have to understand the code for merge sort. You just have to understand the theory. And when I start doing this stuff on the next slide, the theory should be pretty easy to understand. The idea of merge sort is it's easy to take 2 things that are already in order and put them together to make a greater list that is in order. So if you had 2 file cabinets that had patients at a doctor's office, and both those file cabinets were in order, it's fairly easy to merge. Like you say, okay, well, let's take the A's. And you start on one list and you're like, oh, this guy's Apple. And you're like, this guy's Ah. Okay, well, take the file that's Apple and put it down because it's first. Then you see the next file is apricot. So you're like, apricot's less than Ah, so I put that down. Then you're like, Bob. And you're like, Bob is not less than Ah, so put Ah down. And you just follow that procedure over and over. And you're always looking at one item, whatever's at the first of the list, and taking the smaller one. Some notes you should know about merge sort. It's fast. And you wouldn't think it's fast because it's so complicated, but it's fast. The only time merge sort is not fast, is not as fast as insertion sort, is when the data is already or almost in order. So remember I told you with insertion sort, it's going to be the one that's the fastest if the data is almost in order already. Alright, it requires a temp array that is of the same type and size of the array being sorted. The temporary array should be a static attribute. That's all about coding stuff, and you don't really need to know this because we're not coding this one this year. Alright, so an example. Here we have a list of 6 things, and we have to merge sort them. The first thing we do, we don't even look at the list as an order. We say, okay, well let's cut this list in half. We should really have a list of 3, 8, minus 1. The other list, that's a 4 there, it's hard to see under my face, but it's 12, 16, and 4. That doesn't seem like it's done anything. Then they're going to look at these 2 lists and be like, well, those lists are not easy to put together because they're not in order, so we should make smaller lists. And on this step, you just have to be consistent. I don't care if you always give the extra item to the left or the right, you just have to remain consistent. So I'm going to always give my extra item to the left. So 3 and 8. And now I have a list of size minus 1. And we look at that list and we're like, oh, that list is beautiful. It's already in order. Because minus 1 is in order with minus 1. It is a list of its own. It's one piece of data. And that one piece of data is in order. So then we have 12 and 16. Those happen to be in order, but we're not even bothering to check that. Right now we're going with the assumption of we have to split the lists into all one piece because we want every list to be in one piece, because if we have lists that are only one piece of data, we know those lists are in order. So we're going to split the 3 and 8 apart. We're not running any comparisons yet. 3, 8. 12 and 16. Running out of time, I need to go through this a little bit quicker. So what we do here, we look at 3 and 8 and we say, oh, the 3 is smaller, so let's take the 3. Then what happens? That list is now empty because the 3 is gone. So we just drop everything in the remaining list down. So we only did one comparison there. Here we compare the 12 and the 16. We take the 12, we put it down here. Then the left list would be empty, so we just let the 16 drop into place. Now we have to merge these lists together. So we compare the 1, the negative 1, and the 3. We take the negative 1, we put it down, that was a comparison. And then we do 3, 8, 3, 8, because they magically drop into place because no comparisons need to be made because that list is already in order. So then we take these, and 4 is less than 12, so we take the 4. There's nothing left in that list, so we could do 12 and 16. And I ran out of room, so I'm just going to draw these together right here. So down, down, and we say, what's smaller, minus 1 or 4? Minus 1. Then that 1's gone. So now we say, what's smaller, 3 or 4? 3. What's smaller? 8 or 4? 4. Now that 4 is gone. What's smaller, 8 or 12? 8. So we had to run 1, 2, 3, 4 comparisons to get all those numbers in place. Now we just magically drop the 16 and the 12 in place because we don't need to compare to find out who's smaller. We just take the remaining values. And now our list is in order. What you need to know about this is the reason merge sort is fast. It minimizes the number of comparisons that are done, and comparisons take a lot of time. So if you're comparing less items, your sort is faster. So it's minimized comparisons. even though it does a lot of work splitting and merging the lists back together. And that's it.